Hi, this is ATLAS-SPD. This presentation is about ATLAS-SPD, our geometry-aware evidence memory model for long context memory summarization. The task is not only to write a short summary from a meeting transcript. The harder requirement is to answer a query, stay grounded in the right evidence, and remain reliable even when the supporting terms are spread across a very long meeting. We study this on QMSum and ExplainMeetSum. The scientific question is also narrow and deliberate. If we keep the backbone and the training budget roughly matched, does geometry-aware evidence memory add value beyond a strong Euclidean memory baseline? So in the next few slides, I will first define the problem, then explain what SPD means, then show the iterative design path, the fairness control protocol, the final ATLAS-SPD pipeline, and the result with honest interpretation. The project started from a very specific task definition. In long meetings, the evidence needed to answer one query is often scattered. One relevant commitment may appear early, a clarification may appear in the middle, and the final decision may appear much later. That is the lost in the middle problem. The information exists, but the model may under-retrieve it or underweigh it. The second problem is representation. If every chunk is stored only as a mean embedding, then chunks with similar language can collapse together even when they support different claims. A tentative proposal and a confirmed decision can look too similar after mean pooling. So our target was not simply better fluent summaries. Our target was grounded query focused summarization. The output should be concise, but it should also be traceable to evidence in the transcript. This is why our evaluation has four main axes: ROUGE-L-Sum, evidence F1. ROUGE-L-Sum basically measures summary overlap. Then evidence F1 measures attribution quality. Middle recall measures whether the model can recover support from the middle of the meeting. Then position diversity measures whether the selected evidence collapses into one region or stays reasonably spread across the document. So this slide is the conceptual primer. An SPD matrix is a symmetric positive definite matrix, can be thought of as a covariance-like object. Intuitively, a mean vector tells us one average point, but an SPD descriptor also tells us spread, orientation, and internal structure. In the visual on the left, the point is the mean. The ellipse is the covariance geometry. Why is that useful here? Because two meeting chunks may have a similar average semantics but very different internal claim structure. One may contain a tentative suggestion, the other may contain a confirmed decision with conditions. Mean pooling can blur them together. Query condition variance can preserve more of the difference. ATLAS-SPD uses this idea in a constrained way. First, it keeps the whole transcript visible through interval sketch tokens. Second, it preserves the strongest lexical anchors so summary wording does not drift. Third, it builds claim-specific chunk level and sentence level SPD descriptors in a low rank space. Fourth, it uses a balanced transport to select evidence across front, middle, and back region. Finally, it uses a text-first decoder, so the model still generates mainly from the selected text, while the SPD memory acts as a structured guidance. So the key message is simple: SPD is not replacing the language modeling. It is providing a richer evidence representation that helps the model choose and organize support more faithfully. A very important point is that this result did not come from just one model attempt. It came from an iterative research program. We began with GeoEvism to build a stable same backbone comparison. Then we tried full SPD memory that showed that geometry alone was not enough. The branch could be stabilized, but it was not it's strong enough to win. Then Spark introduced band-aware SPD and improved the grounding, but ROUGE still lagged. Then ARC, it preserved lexical anchors and moved to text-first decoding, which recovered summary quality. Then Capri and Bridge added claim conditioning and transport across intervals, which improved evidence attribution and middle recall more systematically. Now, finally, Atlas combined the pieces that repeated survived ablation. So the final model is not a random design. It is a cumulative result of observing specific failure modes and correcting them one by one. Namely the instability, loss of lexical anchors, weak claim separation, poor middle coverage, and low position diversity. So this slide explains why the comparison is actually credible. We use QMSum for query-based meeting summarization and ExplainMeetSum for evidence supervision. The main comparison is among no memory, Euclidean Euclidean memory, and the ATLAS-SPD variants. One important point is that the central architectural comparison is fair. The matched Euclidean control and the ATLAS-SPD use the same backbone. They use the same general training budget, the same state structure, and the same broad receipt. That means the claim is not a large model wins. The claim is specifically about whether geometry-aware evidence memory adds value over a Euclidean evidence memory baseline under similar conditions. This fairness matters because the novelty claim lives or dies on that control. If SPD only wins when it gets extra capacity or maybe extra training, then the geometry argument is just weak. But if it improves evidence attribution and robustness under a matched setup, then the result is much more meaningful. So basically the theoretical intuition is this: mean vector memory is first order. It tells us whether a chunk sits on average, but it does not preserve how information is arranged inside that chunk. SPD memory is second order. It captures spread orientation in representation space. So for meeting summarization, that matters because different parts of a meeting often reuse similar vocabulary while expressing different functions. Say proposal, objection, clarification, decision, condition, and follow-up. Two chunks can have similar mean semantics but different internal geometry. The SPD descriptors can separate them more clearly. A second theoretical point is aggregation. If the memory objects are covariance-like, then comparing and averaging them in the right geometry actually matters. This is why log Euclidean operations are used. They let us compare structured evidence objects more naturally than simply flattening them as ordinary vectors. The third point is retrieval. Retrieval versus generation. SPD structure helps most at the evidence selection stage. So the winning design is not to let SPD dominate the entire decoder. The winning design is to use SPD where the second order structure adds information while also preserving the lexical anchors and text first generation. So here we have the full ATLAS-SPD pipeline. So first we start with the query and the full transcript. From the transcript, we'll build an all-interval sketch, so front, middle, and back region remain visible to the model. That preserves the broad document exposure that made the no memory baseline surprisingly strong. Next, we compute Euclidean relevance shortlist and preserve the strongest lexical anchors. This is the safeguard for summary overlap. The geometry branch is never allowed to throw away all wording faithful evidence. Then we predict latent claim slots. Instead of forcing one global memory to represent the whole answer, the model separates different answer components. For each slot, we build chunk level and sentence level SPD descriptors that gives recall at the chunk level and citation precision at the sentence level. After that, balanced transport selects evidence across intervals rather than over-concentrating on one region. Finally, the decoder stays text first. It reads selected evidence text, interval sketch tokens, and only a small SPD memory signal. So every major block corresponds to one lesson from earlier failures. Keep global coverage, protect anchors, separate claims, diversity support, and let text remain primary for the generation. This slide is the mechanism to metric bridge. So first, memory overlap is preserved because lexical anchors stay in the final evidence packet. The decoder remains text first and the all interval sketch keeps the whole meeting lightly visible. So that is why ATLAS-SPD can stay close to the strongest baseline on ROUGE. Second, evidence attribution improves because latent claim slots separate answer components and multi-scale SPD descriptors preserve within claim structure better than the mean vectors alone. Balanced transport then chooses a more coherent support set. That is why evidence F1 races consistently against the matched Euclidean control. Third, a middle recall improves because band-aware prototypes and interval balance selection keep middle support visible instead of letting all evidence collapse to the boundaries. In other words, the architecture is aligned with the metrics. Anchors support ROUGE, SPD improves evidence F1, and interval-aware transport helps the middle recall. So this is the key result slide. Against the matched Euclidean control, ATLAS-SPD is our strongest SPD result, as can be seen. In the best fair run shown here, summary overlap is essentially tied. ROUGE LSM is also slightly different than the ATLAS-SPD and the Euclidean control, and the interval overlap overlap 0. So I describe that as tied rather than decisively better. Evidence F1 improves substantially. The strongest result is the evidence attribution. So it improves substantially over the fair Euclidean control with a fully positive confidence interval. Middle recall also moves upward and the confidence interval is positive in the strongest ATLAS analysis, which means the model is recovering more support from the middle of the meeting. So the blue claim box is deliberately worded to match what the data truly support. So ATLAS-SPD improves evidence attribution over the same backbone Euclidean evidence memory baseline by roughly matching summary overlap, and it produced the clearest SPD gain we obtained under a fair control. So this is the honest reading. The first remaining blocker is position diversity. Even when evidence F1 rises, the selector can still over-concentrate support in fewer regions than we want. That means the evidence set is not yet as well spread across the meeting as the strongest baseline. The second blocker is the Euclidean mix. The learned mix stays high around 0.94, which means the best current ATLAS model still behaves mostly like a strong Euclidean system with an SPD correction rather than a fully SPD dominant memory. So the next move is now narrow and concrete. Keep the evidence F1 gain, preserve the middle recall improvement, and recover position diversity without giving back the ROUGE. So to conclude, this project produced several concrete outputs. We built a fully designed line from GeoEVSim to Spark, ARC, Capri, Bridge, and finally Atlas. We established the same budget Euclidean fair control, which makes the main claim scientifically more meaningful. We developed a numerically stable SPD training recipe with fail-fast checks. The best honest claim from the current project is this: ATLAS-SPD clearly improves evidence attribution over a matched Euclidean evidence memory baseline, while keeping summary overlap roughly tight and improving middle position recall. So the model does this by combining lexical anchors, interval-aware document sketching, latent claim slots, multi-scale SPD retrieval, balanced transport, and text-first decoding. So the final takeaway is that careful geometry memory design can measurably improve grounded evidence selection for long context summarization under fair control conditions. That is already a meaningful contribution, even though the final full win over every baseline is still open. Thank you.